Hello, welcome to my lecture presentation on Chapter 4, Subtopic 4.5, Metallic Bond. In this slide, I'm going to use the electron C model to explain the metallic bond. According to the electron C model, the solid lattice of metal consists of an infinite array of positive ions immersed in a sea of delocalized valence electrons. These delocalized valence electrons are not bound to individual ions, and they can therefore serve to bind large numbers of metal ions together. According to the electron C model, a metallic bond is the electrostatic force of attraction between the positively charged metal ions and the sea of its delocalized valence electrons. I have here two examples of electron C model diagram. First is for magnesium, and the second is the electron C model for aluminium. When we are drawing an electron C model, the most important thing to observe is the number of electrons drawn in the valence electron C. Take for example, if you are drawing electron C model for magnesium. If you draw 9 cations of magnesium, since each magnesium atom releases 2 electrons, so you have to draw a total of 18 electrons in the C. For aluminium, if we are drawing 9 aluminium cations, and since each aluminium atom releases 3 electrons, so you have to draw a total of 27 electrons in the electron C. So the electrons are forever on the move. That is the reason why we label it as sea of delocalized valence electrons. The word delocalized here means the electrons are forever moving or changing location. The strength of metallic bond depends on, first, the number of valence electrons. The more valence electrons donated to the sea of delocalized electrons, the stronger the metallic bond. Second, the ionic radius. The smaller the radius of the metal ion, the stronger the electrostatic attraction, thus the stronger the metallic bond. So we come up with a general statement that the strength of metallic bond is actually directly proportional to the number of valence electrons per atom and inversely proportional to the cationic radius. The physical properties of metals. First, melting and boiling points. Metals generally have high melting and boiling points due to the strong metallic bonds. I have here a table of period 3 elements consisting of sodium, magnesium, and aluminium. And it's also shown here the number of valence electrons per atom as well as their melting and boiling points respectively. Across the period, the increase in the number of valence electrons per atom and the decrease in ionic radii causes an increase in the strength of metallic bonds. Therefore, across the period, you're able to see the increase in melting as well as the boiling points. In this slide, I will still be discussing about melting and boiling points. I have a table here, a list of group 1 elements. Moving down the group, lithium, sodium, potassium. Since they are in the same group, these elements have the same number of valence electrons. And what you observe here is there is a decreasing trend in the melting as well as the boiling point. The descending a group, the increase in cationic radius results in weaker electrostatic attraction between metal cations and its valence electron C. This results in a decrease in the strength of metallic bond. And that is the reason why the decrease in melting and boiling point down the group. Properties of metal. First, thermal conductivity, and second, electrical conductivity. Metals are good conductors of electricity. When a potential difference is applied across a piece of metal, the delocalized electrons will be attracted to the positive terminal, and that results in a current flow. That is why metal conducts electricity. Metals are also good conductors of heat. When heat is applied to one end of a piece of metal, the kinetic energy of the electrons increases. This energy increase is transmitted through the sea of delocalized electrons to other parts of the metal. So this explains the good conductor of heat of metals. The third property of metal, ductility, and the fourth, malleability. If a metal is strained, the layers of cation withheld by their sea of delocalized electrons slide over one another without any change in the overall structure, overall lattice structure and the metallic bond. This explains why metals are malleable, which means it can be hammered into desired shapes, and also ductile, which means can be drawn into wires. So this is how the ductility and malleability are explained. When a force is applied, the layers of cations slide over one another, but they are still strongly held by the sea of delocalized electrons, which means that the metallic bonding are still as strong. Therefore, metals can be deformed without breaking.